Thank you, Stefan, for the very nice introduction, and good morning. So this is my talk that I presented earlier at the Copper Expert Committee last year in Leuven. So this is the copper case, but the focus today is the tools that we are focusing on, and please think about your application as my talk progresses and think how it can be useful for you. Where is the pointer? Sorry. It's here. Okay. Sorry about that. Okay. So a morning refresh from yesterday's talk. So Moritz introduced the hierarchy of processes and materials. And we have from atom assemblage till process. And Anna mentioned about the microstructure and phase. And today in my talk, I will focus on process and phase assemblage. Exactly 24 hours ago, we learned a lot of different kind of processes from Professor Reuter's talk. I hope you remember some of it. And there are different kinds of processes and different industries, ferrous industries, non-ferrous industries, battery materials, and overall, the extractive metallurgical field faces common challenges here, and some of them I have listed out here. So first challenge is that there is the ore quality that has degraded. So there are like a lot of impurities that are present in the ores. Of course, their goal would be to have stable processes and also to have an optimized feed to be able to receive a high quality output out of your process. Then the next challenge is energy and emissions. The goal would be that we would like to save energy and also restrict the emissions according to the particular limits set by the government, ideally. And then another challenge is to control the process and also optimize the process. And in this case, the goal would be to maximize recovery, so as much as possible materials you can get out of it. And it is not only the things you get out, but also you can increase it by reducing losses so that you have more profitable business model. And then there is recycling, which is a quite hot topic because we want to recycle the waste streams. And in this way, we would also like to support the circular economy and make processes in a closed loop manner. The next challenge is to minimize losses. And we learned from yesterday, from Professor Reuter's talk, that the losses are inevitable. And therefore, we will make losses, but therefore, it is still, we can try to have reduced amount of losses of metals and especially critical metals. And of course, we would like to innovate and reduce cost, and which is why our goal would be to have R&D, to have a faster R&D, and to have lower costs. So all in all, we would like to utilize the current resources effectively, and the tools that we are developing could support you in achieving those goals. And these goals can be achieved by process modeling, and therefore process modeling is important. And now I will come to the tools that I'm going to introduce today. So we learned from the last users meeting in FactSage 8.4 that there are two process modeling tools, FactFlow and FactProSim. I presented a talk on each of those tools, and we also have ChemApp for Python, which is an optional add-on to FactSage customers, or it can be also purchased separately as a standalone product, which is also a process modeling tool. All of these tools are versatile and can be used for any kind of processes. Just the only condition is that you need to have a CST file So as long as you have thermodynamic data contained in your CST file, you are good to go. And for all the processes, the goal is to always run the process under known condition, because they are learning or because they are running on a large scale, in ton scales and so on. So you would like to reduce uncertainty, and you would like to work under known conditions also to prevent accidents and so on. So what you can do with these process modeling tools, so first of all, you can create a digital twin. So whatever you see in your plant, you can create a digital twin of that. You can envision and create your plant flow sheet with different furnaces and so on. You can calculate multiple thermodynamic equilibria. It is not one by one, but you can calculate multiple thermodynamic equilibria just by running the model. And then you can also have streams. You can set stream inputs as you like whatever you obtain in your plant, and also the output after your calculation. You can also do post-processing and so on. And you would like to see how my parameter affects the overall output of my process. And therefore, it makes it important to perform parametric studies. And so you can also vary your parameters and see what happens if my temperature is changed, and so on. And you can also include your experimental measurements, so basically what you obtain in your lab and plant, and incorporate that into your model, and then run the model and see what output do you get, even before you process in actual time. So this step can be before, and you can actually anticipate output based on your real sample measurements, maybe from chemical analysis. So after ICP OES, you can enter that composition, and you can actually foresee what output you would like to get. So all of these tools can be used for all processes, and today I will focus on copper, primary copper production application, but please keep in mind that it can be also relevant for any other processes. So this is the application I will be speaking about today. So, so it comes from CuFeS2, which is the chalcopyrite ore. This is the mineral from the earth. And this is the very, very simplified version of this process. So real life process is much more complex. This is a very simplified process flow diagram. So here you see we have copper concentrate with 8% water that goes into the smelter with oxygen-enriched air and fluxing agent, which is silica. It goes to 1250 degrees Celsius and 2.6 bar. The slag and gas are discarded, and the matte goes further for slag forming converter, and then the matte goes again for the copper making converter, and then we form blister copper. So blister copper, for those who don't know, is a copper-rich phase from which later on in the downstream processes, copper can be extracted for real-life applications such as wires and so on. So this flow sheet you can actually create in FactFlow. In FactFlow, it is super easy. You can just drag and drop the model blocks from there. You can see input, output, and so on. You can just drag and drop, and within each block, you can set information. What is your sample, temperature, and pressure, everything. And then, yeah, the next speaker will be speaking more on FactFlow. And yeah, so this is the version that I used around August, September last year. So, yeah, so here you can see we have smelter, the slag forming converter, and the copper making converter process in the FactFlow. And then you can see that in the output, it is very, very important because copper is used for different applications such as wires, cables, and chips, pipes, and so on. We care about the amount of copper that we form, and we also care about the high amount of weight % of copper in the blister phase. This is very important because it has real economic value. And to be able to get that, we see there are a lot of input parameters such as gas, or amount, flux, and so on. And we have a list of process parameters such as smelting temperature, converter temperature, gas amount, and so on. And all of them individually and independently can affect the output, but the unfortunate reality is that they are entangled, which I will come to later. So even in this simplified example, it makes sense for us to see, I will show you an influence of one input parameter over the output, just so that you get an understanding. So for this, I choose gas input for converter for blister process, so which is up here. And what I do is I have gas, I keep everything same. So oxygen enrichment, for those who don't know, is the amount of oxygen divided by amount of oxygen plus nitrogen. So I keep this ratio same. I just change the gas amount from 20 kilograms to 240 kilograms. I just change the amount of gas, and then let's see what happens. So we get this result in FactFlow, very nice graph, and you can see that I change gas amount from 20 to 240, and this red square thing is the amount of copper in the blister phase. So you see that it increases, then it reaches a maximum, and then it decreases. This is because of over-oxidation of copper in the slag. So we would want to produce more and more copper, so we would like to stay somewhere here. And also you can see that in the blister phase, it is not only copper, but we have oxygen, iron, and sulfur that are also present. And you can also see that somewhere here is where the weight percent of copper reaches a maximum. And therefore, if I am working in a process, then it makes very much sense to me that I operate my process under 180 kilograms of gas input to converter for blister. So now we gain some insights from process parameter variation. So in reality, so this is a study, but in reality, this flow sheet looks static, it's a diagram, but in real life, there is a lot of movement and a lot of flows and a lot of variables that change, and not independently sometimes. Therefore, it is very important to learn these interrelationships, and also we would like to optimize the parameters because we would like to achieve our targets. So the interplay of multiple parameters is required, and this is where ChemApp for Python can act as a versatile tool in order to be able to achieve your goals. And today I will show you how you can do that with ChemApp for Python. And to be able to do that, first I would like to create a process model in ChemApp for Python. So this is the same process model that I have created in FactFlow that I would like to create in ChemApp for Python. So you can see in FactFlow one block here is one line of code in ChemApp for Python. So this line, copper input, and the CASC create STCFS means ChemApp stream calculation, create streams using complex formulas. So this is the short form. And this is the name of the stream. This is the chemical composition of this. Okay, why is it? Okay, yeah, this is the chemical composition of the stream, and this is the amount, 920 kilograms and 80 kilograms of water, and the temperature and pressure of the stream. So temperatures are in Celsius, and pressure is in bar, and amounts are in kilos. So in this way, I can create copper input stream, gas input stream, and silica input stream. Then I would also like to add a furnace to react. And so you can see that I created a furnace calculation. So I do ChemApp stream calculation, isothermal reaction, using all these three inputs as the calculation input for the calculation. And the temperature is 1250 and 2.6 bars. Then I would like to separate these streams, and so I have slag, matte, and off gas. This is the same thing, so it is taking result from smelter result and creating streams based on slag, which include these phases. So it is super easy to create a process model. Then actually in the process, so matte goes further to converter for slag making, and then for a converter for copper making, and then we have a final output. I have not shown code here, but believe me, it exists. Okay, and now we have created a process model based on this process, and I will show you now how we can tackle the metallurgical challenges faced by the industry using this process modeling. So one of the challenges that I mentioned were that the ores are degrading. And so our goal would be to mitigate this challenge, of course. And in reality, there is some pyrite impurity in the ore. And in my example, I have taken 0 to 10 weight % of the ore, which is quite comparable to reality. This acts as an input. And you can imagine if this input is impure, after everything, we will get output will also have an effect. And as a copper producing company, I would not like to have this effect, right? So my targets would be then, I have set the targets to have the blister amount as high as possible, and also the copper weight % in the blister to be greater than or equal to 98, so which is also like very pure amount. And how can I achieve these goals? So let's see. So what I will do is that I would like to optimize the smelter temperature, and this would depend on the pyrite amount in the input feed. And how I did that is that I optimize the process parameter, which is the smelter temperature optimization. And at every point, I would like to achieve multiple targets, which are to maximize copper amount and the weight % to be greater than or equal to 98. And I repeat this optimization at different feeds. And this I can easily do in ChemApp for Python with a very simple for loop. And I performed multi-objective optimization because we have 2 objectives. And there is always a trade-off between the amount and the purity, right? Like we know this. And therefore, you see that I have this Pareto front, which is obtained after multi-objective optimization. And this is the front for a feed of pyrite impurity equals to 10 weight %. All of the points that you see are optimized points, and the color here, so the yellow regions indicate higher temperatures, and the blue represents lower temperature. And all of these are optimized points, but the star represents the target of copper weight % equals to 98, because that is what I would like to achieve, right? So I performed this optimization. This is the result for 10 weight %, but I performed from 0, 1, 2, 3, so until 10 in steps of 1. Okay. Yeah. And to be able to do that, I created a function, temperature in smelter optimized feed for FeS2 variation, and I changed the FeS2 % inside and run this. And you see that the results here at the bottom. So as the blue plot is that as the amount of pyrite impurity increases in my feed, so does my temperature. And it is because the FeS2 has a higher melting point than the CuFeS2. So if I have more FeS2 in my input, then the smelter needs to run at a higher temperature to be able to melt all of that. And also, you can see that as the impurity increases on the orange curve, the total amount of copper that I would be able to extract after this process decreases, which is correct because we are removing essentially CuFeS2 and replacing it with only FeS2. So we are actually putting in less copper in the flow sheet. So if you put less copper, you will get less copper. And so now we can get estimate of optimum temperature at which the smelter should be run for a given FeS2 impurity in the feed. And this number is important for process operators because when they are processing certain impurity, certain feed with a given amount of impurity, they need to know the number at which the process needs to run. And also, you can see that we can realize the amount of copper we can extract at the end of the process. And this knowledge is also useful because you can see if it is making financial sense for your company to be able to run this impure feed. And now we have answered the question of the optimum smelter temperature depending on the pyrite amount in the feed. Okay, sometimes, so in this case, I optimize the smelter temperature, but in a real plant, it not only one lever that you can vary independently, but there are multiple constraints, because if you increase the temperature too high, then your refractory bricks may suffer, then there are other problems. So it is always a good idea to have multiple controls. And so now I have the same challenge of the degrading ore. Just this time I set my target to be weight % greater than 98. And this time I would like to not only optimize the smelter temperature, but also the input gas amount for converter for blister. So now we have an interplay of these parameters. And let's see how I have done it. So I do the process parameter, which is the smelter temperature, and process input, which is the gas input for converter for blister optimization. And I would like to achieve multiple targets, so weight % and the amount targets. And I repeat this optimization for different feeds, so 0, 1, 2, 3 until 10 in steps of 1. So you can see that this is the framework of the results. So you can see on the x-axis there is gas that is existing in different amounts, and also on the y-axis different temperatures. At the top you can see we have copper weight % greater than 98, and this is for 0 weight % of the feed. And now I will show you the result. So I performed Python grid search optimization in steps of 20 with interpolation. The white regions that you see in this square are actually not empty points. They are the points that exist, but they don't satisfy the cutoff of copper weight % greater than 98. So they lie lower, hence they are not shown in this plot. The colored regions are the optimized points which satisfy both conditions, and on the right you can see the copper and blister amount. So the yellow regions indicate that we have large amount of copper, and the dark regions indicate we have less amount of copper. Of course, I would like to have large amount of copper. So it's beneficial for us to stay in yellow-green regions here. And I have done this optimization for different feeds, and if we can show how they transform. Yeah, stop maybe. Yeah, okay. So we have seen how it changes. And you may have observed that we start from yellow-green regions, and then we go more and more bluish because we have more impurities, so we essentially make less copper. Also, what you can see is all these are optimized points. So for any given point, okay, if I can point rightly, yes. So for any given point, we have the optimized temperature and optimized gas input amount to be able to get the right amount of copper here. And you can actually compare your zones of interest. So we have a yellow region somewhere here and somewhere here. You can actually compare that what does it cost me to run my process at 1300 degrees and this corresponding amount of gas, which I think is 180, and also maybe at 1150 with large amount of gas, because increasing temperature costs fuel, and fuel prices we know. And also for the gas amount, it is not only the input gas you need to be able to perform this process, but the after gas, so off gas cleaning part is also very important that we take into consideration. You can find the amounts, you can find the financial estimates, and so on. Also, you would like to perform your process somewhere where there is a larger freedom for you to be able to do that. Like you would not operate your process somewhere here because this region is quite small, right? Like you don't have that much of freedom, flexibility. However, somewhere here and somewhere here would be more interesting. Also, depending on your zones of interest, like you can find zones of interest, and if you are interested to operate your process in this given window, you can find the limits of this window, you can perform more deep analysis and a lot of insights which are very valuable for your operation can be achieved with this. We also saw that both temperature and gas input for converter for blister have an impact on the amount of copper that we would make. But as I increased my impurity, the diagram shifts to the right, meaning that the gas input in converter for blister has larger impact. Both of them have an impact, but the gas input has a larger impact. And when we have more impurity, we need more gas to be able to produce the copper, corresponding copper amount. So all of this information is valuable, and it is not only qualitative but also quantitative. So you can do real, things here. So now we have achieved this answer, and now I would like to conclude my talk. So both FactFlow and FactProSim are free add-ons in FactSage. You can use it. They have process modeling GUI. I demonstrated today some capabilities of FactFlow and mainly for ChemApp for Python. With ChemApp for Python, you can do process modeling with complex multi-parameter process optimization with valuable insights. You can do alternate case scenarios. What if my feed is more? What if my flux is more? And things like this. With this knowledge, you can empower plant operators in finding real values. You can do financial estimations, raw material purchases, whether a certain feed is acceptable for me to be able to process. All this decision-making part can be done. And you can very easily determine your areas of interest and operate in known regions, firstly to prevent accidents, and secondly to maximize revenue and also minimize losses. And the very important message that I want to give is that with the programming power of Python, you can scale this model to the level that you want to achieve. And all of this is already published, the parts 1 and 2. There is a series of 4 blog posts. If you are interested, you can please check GTT webpage and my GitHub account. And we have also performed lead process modeling, and we would be presenting this in this conference. So if you're interested, please attend. And if you have any questions, I would be very happy to answer. Thank you very much.